made all those benchmarks unusable. Or at least it made the heights between them be incorrect. So it's gone. Now we're going to replace all of those 7 vertical datums with 1. The North American Pacific Geopotential Datum of 2022. And on this map, you see that it's covering a quarter of the planet. Actually more than that, because we have places outside of there. We have Guam and Northern Mariana Islands will have their own geoid model, a model for the vertical datum, and American Samoa will as well. But it'll all be consistent, and it'll all go under that name of NatGD 2022. Again, a real push towards consistency in everything. Now, you all have heard of shake and bake, right? Well, we're calling it shift and drift for a modernized NSRS. And the idea is that there's going to be a sudden shift when this thing rolls out. Everything's going to change by a sudden amount. And I'll show you maps of this, but the horizontal change is going to be about a half a meter up to 4 meters, or up to 13 feet. Website height changes will be plus or minus 6 feet or so, 2 meters. And the elevation or arithmetric height change will go from around 0 up to 2 meters, or up to 6 feet. Let me show you maps of that so you get a better idea in a second. That's the shift part. The other part is the drift part. So all these tectonic plates are moving around continuously. That is something that's going to be part of the system. So coordinates can change with time, but we can also use it to lock things down in time as well. The drift actually has another component. The one is, like I said, tectonic motion, tectonic plates moving, but there's also other motions within the plates that are not associated with plate rotation, and there's also earthquakes, for example, those kinds of motions. Those will all be modeled under the drift part. So just to give you an idea, here's a map of the horizontal shift you can expect when this rolls out. These contours are in meters. Here's a 1 meter contour cutting right through very western tip of Florida. And if I go along, there's 1.4 meters going through Arizona right there. So those are kind of changes. You see up to 1.5 meters up here in the western United States and Canada. Pacific a lot larger, right? There's 3.5 meters going through Hawaii. But you get down the Caribbean, it's a lot smaller. It's a half a meter or so. So it gives you an idea of the distribution. One thing you can see right away, especially between North America and the Pacific plate, is how different the changes are on different tectonic plates, because they are moving independently of one another in NAD 83, just like they will in the terrestrial reference frames of 2022. Well, that's a height will change too. So a nice way to think of, you can think of that is, looking at this globe here, like the entire globe, the entire ellipsoid representing the Earth, gets shifted by 2 meters. It's shifted by 2 meters this way on your, to the left on your screen, right? To the positive 2 meters over here. So it goes, the height increased by 2 meters there, it decreased by 2 meters on the opposite side of the world, and there's 0 change right along this contour, which just bad luck. It doesn't pass through any part of the United States. It just misses Alaska. But again, you can see the kind of changes to expect, talking about just shy of a meter lower ellipsoid heights in Arizona, for example. Then there's the other thing, the elevation to orthometric height. Those will also change by a different amount than the ellipsoid heights. It goes from nearly 0 in Florida, increasing pretty regularly across the United States, up to about a meter or so in the Pacific Northwest. And it's about half a meter or so in Arizona. About a foot or so, 1 to 2 feet in Arizona, and they'll decrease. And that GD 2022 heights will decrease with respect to NADD 88. The change will be even greater in Alaska, about 2 meters there. So the drift part, there's 2 parts to it. I mentioned before, one's tectonic plate rotation. So all these plates, as you probably know, they're rotating, they're moving around on there, they're rotating, if you will. And it's a purely horizontal motion. To give you an idea, Arizona's moving in the global frame at about 1.5 centimeters per year to the west-southwest, or about half a foot per decade. And what we'll do is we calculate that, we'll measure that rotation actually, and then we'll apply the opposite sense of rotation to NatRef 2022 so it appears to stand still. The whole idea is to have the coordinates not change with time. It will appear to be fixed to that tectonic plate. But there's going to be other motions too, because the plates aren't perfectly rigid. And as you get to western Arizona and certainly into California, you start getting more deformation. So we will model that. Any of the horizontal motion not captured by the tectonic plates will be modeled. But all the vertical motion will be modeled too. Things like due to subsidence, for example, will be modeled, or glacial isostatic adjustment will be modeled. The whole idea is to be able to get coordinates at any time. So it's going to give people a lot of flexibility over what it is they use. And I imagine most people want to use a fixed time so they keep things consistent, and you will be able to in the modernized NSRS. So summarizing, there's going to be 4 new terrestrial reference frames, 1 new geopotential or vertical datum. And it's going to be, I'm calling it semi-dynamic. All locations will have velocities, that's the dynamic part. But you can get coordinates for any specific date. We can remove those velocities, so that's the semi part. And so coordinates will always be associated with a specific date. You can't say, what are my coordinates? And you ask, what are my coordinates on this date? And for Arizona, we're looking at horizontal changes of, say, 4 to 5 feet when this occurs. Ellipsoid height changes. Ellipsoid heights will decrease by 2 to 3 feet, and elevation, or orthometric heights, will decrease by 1 to 2 feet. To get more information about this, you can go to our webpage, geodesy.noaa.gov. There's a great big new datums button there in the lower right left part of the screen. You click that, another window opens up, and there's all this information about this modernized NSRS. Got all the good stuff in there. That's enough on that. But what it doesn't really have on here is this next thing. Even though state plane is part of the modernized NSRS, we really typically don't talk about it as part of modern. For example, that web page I just showed you, it's sort of its own thing. The key, though, is that it will be based on the 2022 terrestrial reference frame. So those latitudes and longitudes, ellipsoid heights, will come into play with state plane 2022. And some things will be the same. It'll be the same reference ellipsoid as state plane 83, GRS 80, and use the same 3 conformal projection types: Lambert conformal conic, transverse Mercator, and oblique Mercator. So we, meaning me and all of you out here there in the audience, we love projected coordinate systems. A lot of people in NGS don't seem to like them that much. I'm not sure why. But I like them enough that I want to have this bumper sticker made. SPCS 2022, making the Earth flat again, 1 zone at a time. Now that's something to root for. That's something you can fight for. So how will it change? Right now on this map I'm showing up here is kind of combined together is all of state plane. State plane 27, which had 134 zones. The state plane 83 had 125 zones, scattered all over the world like I'm showing on here. What's going to happen for the future? How is it going to change? One of the biggest changes is the system's going to be designed to minimize linear distortion or map projection scale error at the topographic surface, at the ground surface. That's to make the map distances close to what you measure on the ground. With that, it helps to show some cartoons. So on here, I have this globe representing, it's the model that we use of the Earth, an ellipsoid, more or less at sea level. And then above, in most cases above it, is the topographic surface of the Earth. It's certainly true in Arizona. It's above the ellipsoid. Now, for a typical projected coordinate system like state plane or UTM, the projection surface cuts through the ellipsoid like I'm showing here. And you can imagine a light bulb at the middle of the Earth projecting out. This part of the ellipsoid is being projected onto the map grid. But really, people work up here. So this black arc represents the horizontal ground distance. You can see that the grid distance is shorter than the horizontal ground distance, and that's typical for state plane. So the whole intent of state plane 83 and state plane 27 is to design zones that minimize linear distortion with respect to the ellipsoid. That was the entire design philosophy behind state plane 27 and state plane 83. That's how it was done. Actually, and probably the main reason it was, well, certainly a contributing reason for doing it that way is the information wasn't readily available to do it any other way at the time. Those were designed. Now, I could take that projection surface and move it up to the ground surface. You know what I did? I just moved it up. Now my grid distance and my horizontal ground distance are pretty darn close together. But there's really only one point in here where that projection surface intersects with topography where the ground distance and the grid distance are the same. So overall, like in this whole area up here, I mean, it's better than it was. The grid distances and the ground distances are close, but they're not quite the same. So this is part of what we're going to do for State Plane 82. We're going to get a little fancier than just scaling up existing zones. We're also going to change the projection location or projection type so that the projection surface corresponds with topography, and then you get a whole bunch of points where the distortion is essentially zero, and over this entire range you get a very low distortion for your design area, which might be an entire state or part of a state or something else, something much smaller. So again, this is the design approach being used for State Plane 2022 to minimize distortion with respect to topography. So there's other complications to it. It can be a maximum up to 3 zone layers allowed. So every state's going to get a statewide zone. They can have 0, 1, or 2 multiple zone layers in addition to the statewide zone. Most states are going to have 2 layers. Arizona, though, will have 3. So how this works is the states contacted us with requests and proposals for what they wanted. And Arizona was part of that. Arizona submitted 3 forms, 1 request for a statewide zone, which they would have gotten anyway, but still, okay, NGS will design it. But also a multiple zone proposal for a layer of multiple zones that covers the entire state, and a proposal for multiple layers that covers part of the state. And Brian Fisher will be talking about that in his part of his presentation. The deadline to get those designs in is March 31st of next year. And one key thing is within a layer itself, the zones can't overlap. So if it's like a quilt, right? So when they cover the state within one layer, each of those zones cannot overlap. Just to give you an idea what's happening around the country, this is colored so that yellow means a state will have 1 layer, orange means 2 layers, and red means 3 layers. You see there's some states will only have 1. They all have only 1. Well, actually some don't. They'll only have 1 layer. Then there's a whole bunch, most of them, 26 states, that will have 2 layers. And then as you go out west in particular, you get quite a few states that are going to have 3 layers. Now this is probably going to change around a little bit. But Arizona is one of the ones that's going to have 3 layers. It can get, and it's going to be a little more complicated. So this map is trying to show how many zones each state will have. And some will have a very few, and some will have a lot. The white ones on here only have 1 zone, just like today. North Carolina, South Carolina, and Tennessee, for example, have only 1 zone, and they will in the future. And others will have various different numbers. The numbers get pretty big. So the winner so far, if you want to consider them a winner, is Ohio, which will have 89 zones. That's 1 statewide zone plus 1 zone per county for a total of 88, which is on the extreme side for a state that size and with such mild topography. It's showing that Arizona is going to have 36. My understanding that that number is going up quite a bit, actually. So Brian might be able to tell you more about that when he talks. But you can see quite a bit of variety. You can see a lot of states are doing interesting things. All these states that have high numbers, pretty much all the ones that have high numbers, you know, more than 10 or so, they're designing low distortion, or even Kentucky, so it's 8. They're designing their own low distortion projections. They're making small zones to really minimize the difference between grid and ground, and Arizona's amongst those. Now, the one zone that NGS will design for Arizona is a statewide zone, and here's a preliminary map of what it'll look like. Better get cracking here. Just real quick, the colors on here represent distortion. So where it's bright green means it's 100 parts per million distortion. That's about half a foot per mile. So anyway, you see how it's distributed for the state. The idea here is to minimize that distortion at the topographic surface. And even though it's fairly large, it does minimize it for the entire state. And the central meridian is located to help achieve that as well. And we categorize it by population, by the cities and towns that are covered, and by the total state area. Can't dwell on that though, I have to press on. Now there's another category called special use zones, and I bring that up here because That is something that's going to be unique to this part of the world. These are zones that are in more than one state. I'll give you what I mean about that. There's a total of 2. We're going to have in State Plan 2022, it looks like right now, at least initially. One is for the Navajo Nation, and one is to replace the existing Louisiana offshore zone. The Navajo Nation is Arizona, New Mexico, and Utah, plus nominally Colorado a bit. And Louisiana offshore zone is actually Alabama, Florida, Louisiana, Mississippi, and Texas. I'll show you a map. These do not account against the limit on 2 or 3 layers. So here's the Navajo Nation, just to give you a quick picture of it. It's covering a big chunk of Arizona plus into Utah, New Mexico, and they have some property in southwestern Colorado, just like they have this property in Arizona, the Big Okias Ranch. The problem the Navajos have is they're in 3 different states, so and then there are 5 different state plane zones. They're in 2 different UTM zones. It's a terrible mess for them trying to have a consistent geometry for a nationwide GIS. So one thing that was done is a single coordinate system was designed in about 2008, and here's a picture of its distortion map. One very much like this will become part of State Plane 2022. It'll be a little different, but it'll be the same projection type here, a Lambert conformal conic, and it'll be, again, intended to minimize distortion at the topographic surface. And then pulling back some, you see the Navajo Nation over here. You see this big zone in the Gulf of Mexico. That is going to be, well, it's probably going to be called the Gulf of Mexico zone. But right now it's the Louisiana offshore zone, and you can see where it covers, where it impacts 5 different states. That'll be carried forward into 2022. Maybe you heard there's going to be a delay in the modernization of the NSRS. We announced that on June 22nd. The rollout of it will probably be 2024, 2025, so kind of a bummer. But the State Plane 2022 deadlines remain the same. Arizona's still going to have to get the designs in by the end of March 2021, just like every other state. We intend to have everything finalized by the end of 2021 or very beginning of 2022. All the zones will be designed, the parameters can be distributed to software vendors and all that, but it won't be able to be rolled out until the rest of the modernization is done, and it can't come out before the terrestrial reference frame. But even though the designs of the zones will be done, it'll come out along with everything else in 2024, 2025. And I leave you with this thought: patience is bitter, but its fruit is sweet. I think it's going to be worth the wait. Things will be better. What we are finding is we're finding all sorts of things. We're getting rushed into getting this done with all the things that have happened. It's been impossible to be able to roll this out and do a top-notch job doing it. And you can go back to that new datums page to find the FAQs about this as well. So summarizing State Plane Coordinate System of 2022, it's part of the new datum change to replace State Plane 83, same ellipsoid, same projection types. Remember, I told you what the coordinate differences will be in latitude and longitude and elevation. Here, the minimum difference in coordinates is 10,000 meters or 33,000 feet. They will change by at least that much in any zone, just so people won't mix them up in the future. And we did the same thing from going from State Plane 27 to State Plane 83. And again, we're minimizing distortion of the topo surface, not the ellipsoid. NGS is designing a statewide zone for Arizona. Arizona will design 2 multiple zone layers. Consensus is required for the stakeholder designs. That means every stakeholder that voices their opinion has to agree with what Arizona submits. And more information, again, is available at the odyssey.noaa.gov webpage. There's a State Plane Coordinate System link. And I think I should stop there and maybe allow Jack to jump in on this. I'll escape out of that if I can. Whoops. I'll stop sharing. Yeah, Jack will need to share. And if he can't, I have his. I mean, if something goes wrong. All right.
Hey, Jack, you have the ball, so you can share your screen.
Yes, can you hear me?
Yes.
Yeah.
How is it that I'm not able to see my own slides? Can anyone see the slides?
No, you're not sharing.
How about now?
Automatic, Jack, I can watch mine. Oh, there you go.
All right. Always a little bit of technical difficulties when you hand these things over. Well, thank you, Michael and Jamie, for the introduction. I have 5 very brief slides. One of the things that I really want to talk about is these low distortion map file designs, and this is one of the end products that we envision through the work group here at AGIC to make available to our AGIC members, because visualizing a lot of this data, as you've seen in Michael's presentation, is key to understanding it. And one of the things that Michael hit on is accessibility, and part of our accessibility plan is to make these designs available. So I'll get started with these very brief slides. I just want to start out by talking about 3D data, which is available through the continuous in the United States. In this example here, I've taken 36 geotests, and I've mosaicked them basically into one single image data set to create the statewide image that you see here. And to give it a little bit more meaning, we're able to take the statewide data set and then classify it according to elevation value, lowest to highest, and provide a color map to it. 3D data is available. I encourage people to go look at it. It's sometimes very helpful, nice image data sets to work with if you like working with imagery. Moving on, the LDP design software that was used, that Brian will be talking about in his presentation shortly, creates what we refer to as distortion geotiff files for each state plane zone that we design, along with the projection parameter files as well. And all that information is, again, planned to be made accessible at the AGIC website at some point in the future. We haven't got to that point, but that's part of our long-range plans. Currently, what you're looking at here is Santa Cruz County, which had 2 basic geotiffs that were part of the design, LDP design. And what was done, the distortion files were clipped by the zone boundaries for State Plane 2022. Moving on, the distortion files are then used to create a GIS map designs. Distortion files then are classified according to a predefined linear distortion layer file. Michael spoke quite a bit about this, but most of our design parameters that Brian will be talking about, most of our designs ended up in this 20 to 40 parts per million design criteria. And as you can see, that's 1 to 2 tenths per foot per mile. Here's what the distortion images look like as they're added to our map with additional countywide transportation, PLS, and maybe even city population centers will be included in the map designs. And you can see the 2 designs, east and west Santa Cruz County, and you can see that most everything here is in green. Up in these high mountainous areas like the Santa Rita Mountains south of Tucson, there's not anticipated, there's really not any private land up there, so those higher distortions won't really have too much of an effect on their area. Population centers were a big part of the design, as well as ADOT highways and roadways. That's where all the work occurs, and that's where all the people live. So the final designs are going to look somewhat like this. They're going to be, we'll probably have them as PDFs. We'll probably also have source data that people want to take a look at it and work with it themselves. It'll have the projection parameters included along with the linear distortion and a map where the zones exist in Arizona. And then there are graticule lines for the coordinate system around the edge of the map, as well as latitude and longitude. And that being said, this is the final slide. All final map designs along with the state plane coordinate systems for 2022 and the projection parameter files will be provided to AGIC and the end users and stakeholders. That's a big part of getting people to adopt these systems. And I imagine that at some point we're actually going to have people, as Michael indicated, a lot of these designs are going to end up in software in the future, and we'll probably have future get-togethers through AGIC to teach people how to take advantage of these state plane coordinate systems. And that's all I have. So I'm going to stop sharing. And does it go back to Michael?
Thanks, Jack. Yeah, Jamie will hand it off to me, and I'll be able to put Brian's slides in play.
And while you're doing that, Michael, can everybody hear me?
Yes, I hear you well.
Okay, good. I'm assuming everyone else can hear as well. Okay, so I'm just going to kind of dive right in.
Yeah, and so everybody should see your first slide where it says AZ SBCS 22 design criteria.
Yeah, okay, so this slide is a little bit of a mess, but what we're trying to convey is that we've got 3 layers, as Michael had alluded to earlier. So the bulk of what we'll be talking about here in the next slides is going to be the complete coverage layer, and then Jack just showed you a portion of the complete coverage, which would have been down in Santa Cruz County. So that's the quilt that covers the whole state with a zone tile or quilt that they all connect together like one big jigsaw puzzle. Michael had also made reference to originally where we're going to have about 30 some odd zones. That number did change. If you click one slide, Michael. Originally we had said about 30 zones in that layer 1, the middle layer, and about 15 zones in that partial coverage. Once we got into designing, we noticed a lot of the partial coverages shifted over into the quilt, as it were, and right now we're sitting around the 50-ish number for Arizona, plus or minus a few. And before you get too much sticker shock on having a whole lot of zones, bear in mind also that we are eliminating, or the intent of this project is to eliminate every time a surveyor goes out to do a project, they create their own modified zone, which virtually gives you an infinite number of zones, or many, many, many hundreds or even thousands. So having a number like 50 is actually really good, just to put it into perspective. And also the design criteria, we'd originally gone out with some pretty aggressive design criteria for these zones. That's another reason why we had quite a few. And that was 80% of the time we're trying to have less than 20 parts per million out on the ADOT highways, with provision the other 20% of the time not really going over about 40 parts per million. So that's a pretty aggressive design goal, and we attempted it. It didn't work out perfectly, especially in the mountains, and so we did revise that later on. I have a slide coming up that talks about that. But before I leave this slide, I just want to make sure that everybody's aware we've got, the 3-layer system. So if you have data that covers the whole state, the statewide layer is absolutely the one that you can take advantage of. Even in a county, if you have like I don't think there's a single county in Arizona. I'd have to check my notes on that one. Yuma, maybe. Yuma County, I think, is the only one that actually has a single zone that covers it, even though the current version has that zone going into Maricopa County also. But most county-wide approaches, or if you have county-wide sets of data, you're probably going to want to use the statewide zone so that all of your data is on one layer if that's how you need to interact with it. The polling that we had done with most of the, I'll call them surveyor engineering level type projects, was that they're not that big usually. Usually you're doing 10 miles of road improvement, or you're doing 1 square mile of some sort of capital improvement project. So the fact that you don't have a single zone for a county, or even I think most cities have single zones. We didn't necessarily split on cities, but we're having a lot of these options in this layer 1. I don't anticipate it's going to be a problem for anybody. As long as the users pay attention to the fact they've got more than one layer option. And then at the end, we're hopefully going to have some questions, and I'll field any questions on that. Michael, go ahead and go ahead to the next slide. Okay, so this is a lot of these slides are sampling from a much longer presentation that I was having with various surveyors directly, but I went ahead and included a few of these. The 20 part per million, just to give you a comparison, my wonderful cartoon graphics here, really is only about a 800-foot of topographic relief window. So every one of those bands of color in that slide right there represents plus or minus 20 parts per million. And if you're trying to have most of your project, which is the brown line, that's the topography or the highway, as it were, if it's mostly going to be in the green, you can see if you go over a mountain peak, that's where that notion of having 40 parts per million only about 20% of the time. So, you know, like they have a little mountain peak that's in there, but most of the roads on a single zone. Go ahead and switch to the next slide. Okay, so this is just zooming in on that. And another big thing to look at here, and any surveyors that are in the audience, the notion of having state plane not being where you want to work or ground is a very familiar subject. And they, you know, typically you would refer to that as, you know, they would modify state plane in order to be able to use it for their more specific purposes. And they use a thing called a combined grid factor, or CGF, to do that. Well, in the new state plane, the combined grid factor of a low distortion projection is 1. Grid is ground. So you've eliminated that whole process. And then I went ahead and threw some of the numbers on here. I hate putting math in a presentation because it is always complicated, but this is the multiplier. So if you multiply any number by 1, it is just the number. And then even the statewide zone, as long as you don't need super, super high precision of your map distortion, it still has a scale of 1. Is what, you know, what you end up having. So it's like all of these LDPs, all the 3 layers are going to simplify the mathematics greatly, which is a wonderful thing. And then as as your requirements get more and more to unity, or you have less and less tolerance of what you can accept in map plane distortion, you're just going to drop down into these other layers, like the layer 1 layer, which is the quilted layer for that more specific project. And then typically projects, when they do that, they become smaller, and so then they lend themselves very nicely to having a lot of these zones. That they have a lot of overlap, in other words. So let's go ahead and click to the next slide. And then mostly, again, this was like an ADOT requirement. We noticed that there's a lot of hills and a lot of canyons in Arizona, and more than just the Grand Canyon, like Salt River Canyon and the Muyon Rim, the rim coming up out of Verde Valley, lots of different mountains that we either have ADOT highways that go to the top of. Several observatories in Arizona. Kip Peak is one of them. Mount Graham has several highways on it. And so it's like we ended up having a lot of these very challenging segments. And so we rewrote the requirements a little bit midstream there. And essentially when you get into these mountainous areas, we allowed for a little bit more distortion in our design because we didn't want to have 200 zones. We wanted to keep the number down to something reasonable. So we just changed our expectation of that distortion that we're going after. But still, we're shooting for less than 100 parts per million, even in these mountainous type areas. And then in the other presentation I had, there's also some other complexities that you have when you have extremely slopey environments. They tend to cause their own quote unquote distortion as well. So these parameters I think are really rock solid. They're a good functional thing to go after. They provide a lot of performance for many, many users. But we did do that, so you get, like in the graphic I have here, where you get, steep mountains, or they could be steep canyons. You loosen up the requirements a little bit and allow yourself to have a larger coverage. And go ahead and go to the next slide. Okay, so just looking at some of the data that we're using population data to make some of these decisions. We're obviously using the county boundaries to make the decisions. Where the zone boundaries were. Also, we got into like the first slide that Jack showed you, which was Santa Cruz East and West. We discovered that it was hard to describe some of these areas as like East, West, North, South. Specifically, things like Coconino County is enormous. It's in the top 10 largest counties in the country. Actually, I think Arizona's got several counties that are in the top 10 largest counties in the country. So we have really, really big counties. And so we did start prototyping some different way to name these, and we ended up naming them after cities, but that'll come up later here. So instead of calling it Santa Cruz East and West, we called it Nogales, and I forget the other town we used off the top of my head, but Nogales was one of them. And so go ahead and click to the next slide. And we also looked at land ownership, which is represented over there on the left. The graphic's not super good, but you can see it is complex. There's a lot of native nations, a lot of mixing of private and state, lots of big parks, lots of military. So there's a lot of diversity in the land that was out there. And then also the other graphic I have here is just the ADOT highways. And you can see ADOT highways are pretty much all over the place. So that really became a driver in the designing. Go ahead and switch to the next slide. In here, and then this is a relatively current version of what the zone boundaries are. The one on the right is Michael fondly referred to that as the dogger's breakfast slide because it's kind of a jumbled cartographic presentation. But Jack helped me with my presentation on the left there. So they're basically the same data. They're just represented in different ways. But you can see that there's a lot of irregularity, to put it one way, in the zone boundaries. And go ahead and switch to the next slide. One of the biggest reasons you have irregularity is because of topography. So then, I'm not going to read this entire slide in the interest of time, but I'm going to try to hit some of the highlights. The naming convention that we went with, and then you can see Santa Cruz County down there. So Nogales and Sonoyta and Sinaloa, I think if I remember right, there's three little zones that are down there. That is to meet the requirements to have ADOT highways within the zone parameters that we're shooting for. Looking just to the east of that in Cochise County, you can see things like Bisbee or BSBE. That's up on top of a mountain. So the reason it has a little tiny zone is because it is a mountain peak. And there's a highway and a community that are up in there. But then Douglas, nominally the south half of Cochise County, you can see the northern line of Douglas is not a nice, clean east-west line. It has a lot of shape to it. And at first glance, that shape looks to be very irregular. However, when you zoom in on the actual land ownership and the topography, it's following very natural dividing lines, where I don't have a pointer, but you can see there's some darker brown mountains that it's paralleling in the northeast quadrant of that Douglas zone. And that's not only following topography, because that's a mountain range that's in there. It's also following, that's good, Michael, that's right the area I'm talking about with your pointer. It's also following a division between private and federal land. So when you get into the minutia of how these zone boundaries are divided, they actually are very logical to a lot of illogical seeming kind of things that are already there. Where it's, land ownership, as all of us are well aware, it can be very complicated, as can topography. So it's, but anyway, go ahead and flip to the next slide. So again, just kind of, why are those zones irregular in shape? It's predominantly driven by topography. Arizona is an extremely bumpy state with lots of extremes in height and depth. And these zone boundaries are, again, they're following where we could county lines, because those are nice and intuitive, but typically they're going to break into a lot of things where they're following county lines or they're following federal boundaries, which could be parks or nations, et cetera, and definitely following major topographic features. Because those, again, are one of the biggest factors when it comes to driving the distortion that's in the background of that map in the first place. And then go ahead and go to the next slide there, Michael. So are zone boundaries iron lines in the sand? No, they're not. They're more of a suggestion. I give the example of the international date line over here on the right. It's the international date line, in the simplest definition, is the 180th meridian, which is right out in the middle of the Pacific Ocean. However, it crosses any number of countries. And so the suggestion of having the date line at the 180th meridian, in practice, has quite a lot of undulation where people are extending the zone one side or the other. You know, because we go from north to south, you can see the Aleutian Islands off of the Alaska right there is in one date. It's in multiple time zones, but it's in one date. And then further down, there's that nice little key shape, which is the Cook Islands out in the middle of the Pacific there. And so the Cook Islands are entirely on the westerly side of the date line. You know, but it's, go ahead and switch to the next slide. So, and I've got my Black Knight in there, you know, for the Monty Python reference, but, you know, the zone is more of a suggestion. It's just but a scratch to go over the top of the zone boundary. So, you know, as an example, I've got something up here on I-40 in northern Arizona between Holbrook and Flagstaff. And now we've got the coloration, or the color gradiated map distortion, green being plus or minus 20 parts per million, that lighter green color being 20 to 40, or yellow also being 20 to 40, where the one is the grid is below the ground, the other is where the grid is above the ground. And so the area in question is that dark blue line that runs up and down, or north and south in this picture. And if you were to extend either to the west out of the Holbrook zone or to the east out of the Flagstaff zone, you can see you have many, many miles that you could extend the zone and still be within your zone design parameter, being less than 40 parts per million. And kind of the highway line, or the blackish line that's running east and west, which is I-40, where it makes that little dip, that is a rough area right in there. Well, if you had an improvement project that was coming from Holbrook and ran 10 miles to the, or in this case 5 miles, you know, past the rest area, you could put your project all in one zone. And then vice versa, if it was coming from Flagstaff and running to the east, you could have gone upwards of 15 miles outside the zone. Now, these are general numbers, and in practice, some zone boundaries are much more malleable than others. I don't have graphics of them, but you know, picture like the Mogollon Rim, you know, coming from you know, Payson going north. When you get to that feature, the rim is pretty much the line. That's it. The projection that's downhill and the projection that's up on the top. Once you go over the edge of the rim, that's it. You only have, you know, a mile maybe in either direction before, you know, it's a very specific line because of topography. But then you get out into like I-10 as you're traveling from Maricopa County to California, as it were. I mean, it's dozens of miles which these projections are functioning in because the gradient of the ground is so uniform. It's very, very flat. So the example I have on the screen right here is just kind of like an average example, but all the zones do have some amount of overlap so that they do allow you in the scale that they're designed for. Again, you know, the scale is to handle these multiple mile projects. But go ahead and let's go to the next slide. And I've got 2 slides left to go. So now we'll talk about northing and eastings a little bit. So Michael had made reference that the northing and eastings need to differ by, I think it's 10,000 meter, or, you know, the 30-ish thousand foot level. So historically, the graphic on the right, the red stuff is coordinates and systems that already existed. So state plane in this graphic is a little red state of Arizona. Well, all NAD 27 and NAD 83 data pretty much existed as a overlapping system on top of itself. And then the other one that Michael's pointing to right now is UTM. So all of that existed over the top of itself, basically. And what I'm proposing in brief is the graphic that's in the upper right-hand portion of the screen having 8-digit coordinates in feet in both the northing and the easting. And then that does several things. One, it makes it to where we have unique coordinates. 2, it also makes it to where coordinate zone data doesn't overlap itself anymore. Every single zone would have its own unique piece of spatial real estate, as it were. Go ahead and click to the next slide. And then we're going to kind of zoom in on that notion. So here, as an example, the statewide layer would be all within, just in the northing, 20 million feet to 23 million feet, and the easting 10 million feet to 12 million feet. And so all of Arizona would exist on that, all of Arizona's complete coverage or layer 0 would exist in that spatial area. And then when you went to layer 2, as an example, starting with the one just to the right of the Arizona would be Ajo, Santa Rita, Kitt Peak, Tucson, Mount Lemmon. You can see all of those. That bottom row is Pima County. So just as an example, this is preliminary. This isn't the final where everything falls into place. But just as an example, if you were only in a CAD environment or you only had a printout of the data, then it would you would be able to see numerically or spatially which zone you had, irrespective of what metadata you were given. I'm not saying I would advise people not including metadata with their data. That's absolutely not what I'm saying. I'm just saying we're building into the coordinate system some safeguards that, in the hopefully non-eventuality that you don't get any metadata, but at least if, you can kind of do some just glance at the data and have a general idea of what you're dealing with spatially, that's been built into the coordinate system. And then also, you can see a couple other zones that are much larger, like the Colorado River zone, which runs basically from Lake Mead all the way down to the Gulf of California. That would have enough spatial real estate to be unique. Or the PHX zone, that's the bulk of Maricopa County. That zone would have, because it's so wide, it runs all the way out to near Quartzsite. It starts at Lake Roosevelt and runs at Quartzsite, east and west. I mean, it's over 1 million feet in width, but it has enough spatial real estate to be able to exist. So I kind of ran along there, but are there any questions? That's the last slide I had.
Thanks, Brian. I think some have come through the chat, right, Jamie? You got some there?
Emily asked if she will need to reproject her data to the new modernized system.
Well, so the short answer is you don't have to do anything. We can't make people do things. However, if you want to bring your data into the modernized NSRS, and there'll be numerous benefits for doing so, it's more than just reprojecting. NGS will build, we have something called the Coordinate Conversion and Transformation Tool, NCAT, and you can use it to do that very thing, and we're going to add all of this stuff into it. So you will be able to transform from any previous NSRS datum or projected coordinate system up to the modern one and back and forth and all that sort of thing. We will make the tools to do it, but that's actually a very complex topic if you want to get to highly accurate transformations. I hope that answers it.
We're running short on time, but if anybody has any questions, if you want to either type it in the chat or we probably have time if you want to unmute real quick and ask. We've got some questions coming in, or some thank yous coming in. Also, Ryan Barton was excited that you're doing the Navajo Nation one.
Yay, Navajo Nation.
Okay, well, if there are any more questions, thanks everybody for attending, and thank you especially to our presenters, Michael Dennis, Jack Avis, and Brian Fisher. Don't forget we have sponsored breakout sessions next for a half hour, and then at 2:30 to 3, there's a group activity, a little chance to network and do some chair yoga. I've not tried that myself, but it might be fun. And I put a link in the chat for the session survey. If you'd like to provide feedback for the survey, please go to that link and fill it out. Thanks, everybody.
Thank you, everybody.
Thank you.
Thank you.